Section 6.1, area between curves. All right. So back in chapter 5, when we introduced the integral, one of the contexts that we gave to the integral, or one of the applications of the integral, was finding the area under a curve. All right. And when we said area under the curve, what we actually meant was we were looking at the area bounded by the curve and the x-axis. And then we had a whole discussion about positive area if the graph lies above the x-axis. We had negative area if the graph lies below the x-axis, right? And then we also got into eventually that whole net change theorem idea, to where if we had area above the x-axis and area below the x-axis over our interval, we could talk about the net change, right, or our net area ultimately, which was the difference between the two. We also put that in the context of displacement. We said if I just evaluated the integral over the entire interval. But we also brought in the idea of calculating total area or total distance traveled, right? To where if I broke the interval at the point where the graph went from above to below the x-axis, and so we calculated the integral over each of those subintervals, and then where the interval over the interval where it was below the x-axis, which gave us negative area or negative quote-unquote distance traveled, then we slapped absolute value on that, and we could use that to calculate the total distance traveled. Right? That was that whole net change theorem thing. All right, but bottom line was, back in the context of a single function, it was the area between that curve and the x-axis, right? And so it could be positive, it could be negative, depending upon if the graph is above or below the x-axis. Here, we're looking at the area bounded by two curves, right? And since we're no longer using necessarily the x-axis as one of our boundaries, so say y equals f of x and y equals g of x, right? The area bounded by these two curves is always going to be represented as a positive value. Now, we're also going to have to take kind of into consideration that same type of issue we had before, where, if the graph was above or below the x-axis, positive versus negative area, there's going to be something similar here that we'll have to address, but we'll deal with that a little bit later on. All right, so we'll start with the basics here. But the idea is, look, I've got this region bounded by the curves y equals f of x, y equals g of x, and then I also have these two boundaries, these two vertical lines, x equals a and x equals b, kind of serving as our interval. All right, so I'm looking at the region bounded by those two curves over this interval from a to b. And it's a similar idea from before, from that point forward. I mean, we could form the little rectangles, right, like we did previously with the area under the curve. But in this case, the height of the rectangle would be whatever the difference is between f of x and g of x, right? So what is the function value for f at that point minus the function value of g at that point, and that gives us the difference between those two, or the height of our little rectangle. And the width of our rectangle is still delta x, right? Whatever you want to choose delta x to be. Now, we're not going to play approximations like we did before. We're just going to be here interested in the integral and doing a calculation for the area between the curves. We're not going to do approximations with these like we did the midpoint rule and all that with the area under the curves before. So we're going to focus strictly on actually finding the area, okay? But again, I think from that standpoint, it's pretty straightforward. I mean, this is not a big stretch from what we've already talked about, right? So just instead of area under a curve, what's the area between the two curves, where the height of the region is the difference in the function values, right? So, or difference in the functions. So we're going to say that A is the region bounded by the curves y equals f of x, y equals g of x, and the lines x equals a and x equals b, where f and g are continuous. There's our good old continuity again, right? We need continuity over our interval. They are continuous functions on the interval from a to b. And also notice that our function f of x over the interval in question is always greater than or equal to our function g of x, or in other words, the graph of f lies above the graph of g over the interval in question, right, for all x in our interval from a to b. Then I could say that the area bounded by those two curves is given by that integral from a to b, of f of x minus g of x. Right? So the only difference here is instead of just integrating with an integrand of our function f of x, it's the difference between our two functions f of x minus g of x. Now, for kind of leading to what's going to come for our discussion later, since f of x is the function above or the function on top of the function g of x, when we're calculating that height that we're doing here, we always want to take that upper function minus the lower function, because if we want to represent that area as a positive value, then I need the height to be a positive value. All right, so we're going to always take the function that lies above minus the function that lies below. So you can kind of maybe see what's coming down the road. What if that happens to change over our interval? And maybe at some point g becomes the upper function and f is the lower function. Right? So then we'll have to take that into consideration. Okay? So we'll progress to that point, but that's the basic idea. I want the upper function minus the lower function to give us a positive height, and then delta x, or dx. So the integral from a to b of f of x minus g of x dx. So for example, we could find the area of the region bounded above by the function y equals square root of x plus 2, bounded below by the function y equals 1 over x plus 1. It's a funky little equal sign, but that's what it is. Y equals 1 over x plus 1. And by the lines x equals 0 and x equals 2. So there are our limits of integration, right? There's our integral from x equals 0 to x equals 2. So in general, right, so what we need to know is, and in this case we're told, but in general I would have to know that over the specified interval which function lies above and which function lies below, so that when I set up my integral, I'm always going to subtract the upper function minus the lower function. Right? So you may need to graph it to get a visual, right? And if it's not specified, which of course generally it will not be, but we're told in this case that we are bounded above by y equals square root of x plus 2. We're bounded below by y equals 1 over x plus 1 over our interval from 0 to 2. If you graph those two functions, I have the graphs kind of sketched out here on the left. And so that visually shows us that x square root of x plus 2 does lie above 1 over x plus 1. So then I'm just going to integrate over our interval from 0 to 2, right, limits of integration, of the upper function, square root of x plus 2, minus the lower function, 1 over x plus 1. Okay. Now, for these, I am going to allow you to set up the integral and then use your calculator to calculate the value of the integral. In other words, I'm not going to require that you go through and do the old integration and all of that, because these get a little bit ugly, and really for some of the integrals that we're going to run into, you don't actually have a process for finding an antiderivative yet. Okay, so we're going to just use the calculator. I'll show you how to do that, to do the approximation of the integral. And then of course you could use this at any time to check your work on any integral that you have evaluated to make sure you do get an exact or correct value. Right? So here's what you do. Once you set up your integral, right, now don't worry about the two individual functions. Once you set up the integral of f of x minus g of x, then it's a matter of evaluating the integral, right? So that's what we're doing here. So I'm going to put my integrand, square root of x plus 2 minus 1 over x plus 1, into our y equals editor. Okay. And then go ahead and graph it, just to give yourself a visual. Now remember, what are we graphing here? We're graphing this entire function, right? We're not graphing the individual functions that we have graphed up here, all right? We're graphing our new integrand, which is the difference of those two functions, right? So the graph that you get here is going to be different from graphing the two individual functions, right? Kind of keep in mind what it is that you're actually graphing. So I went ahead and entered my integrand into y1. I went ahead and graphed those. I have those graphed on the standard viewing window as usual. And then we're going to evaluate the integral. We're going to calculate the area under that curve from 0 to 2. So you'll go to that calc menu. We've used that before to do intersection, right? So your second trace, that calc menu. And if you look at number 7 under that calc menu is the integral of f of x dx. So go ahead and select number 7, and it'll bring you back to your graph, and then notice it at the bottom it will say lower limit. Let me change this. At the bottom it says lower limit. So enter in the lower limit of your integral, which is 0. So I just typed in 0. Hit enter. It will then ask you for the upper limit. Just type in your upper limit, which in this case is 2. Hit enter. And notice it gives you the approximation of the area under the curve. It also shades it in on the graph itself. Right? And so there's the approximate value of that integral, approximately 2.349103. I approximated it up here to approximately 2.3491. So however many decimal places we care to go to. All right, so it's a pretty quick process for evaluating integrals, but you do have to set up the integral. I will ask you for that, and then you can use your calculator to go straight from here to there and just give me an approximation. Okay, so save you a little bit of work with some of these. All right, consider the next situation. I will take a step forward where here all I'm given are the two functions, and we'll say, okay, here's our function y equals f of x, y equals g of x, and we're interested in calculating just the area enclosed between the two curves, right, without giving a specific interval or any other information. Okay, so I'm looking at a region. I have that labeled as A, the region bounded between those two curves. So A is the area enclosed by y equals f of x and y equals g of x. If I'm going to calculate the area enclosed between those two curves, what I will first need to determine is what are these points of intersection. All right, where do these, what is the interval over which that region is enclosed, right? What are those points of intersection at the beginning and end of that region, right? So we need to find those points of intersection. And then we need to also determine, as we said previously, which function lies above and which function lies below, right? So what is my top function and bottom function? Maybe call them y sub t and y sub b, just to give them a notation, the top function and the bottom function. And then once we have that determined, then we'll just set up our integral as before and do our calculation. So for example, let's find the area of the region enclosed by the curves y equals x squared and y equals 4x minus x squared. And I'm going to go ahead and graph them. And you know enough, I think, about those two curves without even necessarily having to graph them to know which one is which. And in terms of, you know what the graph of x squared looks like. That's our basic, parabola, this guy. And then the other one we know is a parabola that opens down, 4x minus x squared. And so, of course, you obviously need to distinguish which function is which when you graph them. But we can visually see that there are 2 points of intersection between those two curves, and the region that's bounded between the two over that interval, our top function is 4x minus x squared, and the bottom function is y equals x squared. Okay. And again, I'm just getting that visually from the graph because I am looking at this region enclosed between the two curves. Now we also need to know the points of intersection, right? So we know what interval we are calculating the area over, right? So what interval do we need to integrate over? Well, finding the points of intersection, you can do that one of two ways. We've done intersections before on the calculator, back when we were doing the epsilon delta things, and we were graphing a function, and we graphed horizontal lines, and we found points of intersection. So you can use your calculator to find those points of intersection. Or you could also just set the two functions equal to each other, right? Because we know that the point of intersection would be an x coordinate for a point that's common to both graphs. So you could also algebraically just set the two functions equal to each other and solve the equation. So that's what I did here. I said x squared equal to 4x minus x squared. Now, of course, you don't always end up with an equation that's easy to solve. So in that case, you may want to go ahead and use the calculator and get some approximate points of intersection to serve as your limits of integration. Now, all I care about here are the x-coordinates of those points, right? Because I am integrating from left to right in this case. So I'm interested in the x-coordinates of those points to set the boundary for my integral. All right, so whether you do it on the calculator or whether you do it algebraically, if that's not too difficult, in this case I do end up with points of intersection, x equals 0 and x equals 2. So then we'll set up our integral from a to b of our top function minus our bottom function as the integral from 0 to 2. We said our top function was 4x minus x squared, and our bottom function was x squared. So here's our integral from 0 to 2 of 4x minus x squared minus x squared. Or if you wish, if we could go ahead, if you want to simplify that, of course, you can put it into the calculator as written, or you may want to go ahead and simplify it first just to a little less to type in. So this would be what, 4x minus 2x squared if we want to go that route. Either way. Dx, and then we can plug that in, right? But you don't necessarily have to simplify it, because all I'm asking you to do is find an approximation, right? Not actually calculate doing the whole antiderivative and all of that, okay? So this one comes out to be approximately 2.67. And if we wanted to talk units, we are finding area here, so square units, right? So in a real world type application, if we had units involved. But that's the idea, right? So I need to know points of intersection, I need to know which function lies above which over our integral, set up the integral, and then plug it in and calculate. So again, pretty straightforward, right? I mean, there's nothing too tricky here. Here's the next progression, and I guess at the top, as I said, it's not always easy to find the points of intersection. So like I said, you could use the calculator to find those points of intersection as well. Oh, and before I get to the next graph, in this section there's an example 4, because I just wanted to bring this up as a kind of a reference back to the context. Like we said, what does the area under the curve represent? We had it mainly in the context of if it was the area under a velocity curve, right? Then the area under the velocity curve represented the distance traveled by an object, right? So this example 4 on page 430, if you want to reference that, and I brought it in here, gives us the graph representing, shows us the velocity curves for two cars, A and B, that start side by side and move along the same road. The question is, what does the area between the curves represent? And I'm not interested in the whole midpoint rule stuff, but simply what does the area between the curves represent? If each of those is a velocity curve for each of our two cars, we call them car A and car B, right? And so the area between the two curves, right, this area, what would that actually then represent in the context of what those graphs represent? And you should be able to answer that. Because again, remember, what does the area under the curve represent? It's the distance traveled by the car. So the area under the graph of A, right, all of this would represent the area, the distance traveled by car A, right? The area under the graph of B would represent the distance traveled by car B. Right? And so, of course, if we take the difference between the two back to the area between the two curves, then what should that represent? That should represent the difference in the distances traveled, or in this case, it would be how much farther car A has traveled than car B. Right, so again, it just gives a little context, right? An example with a little context back to our whole area under the velocity curve representing distance traveled. So the area between the two velocity curves would represent the difference in the distances traveled, right? So, and like I said, in this case, it would be how much further A traveled than B, because A is above B. All right, so it's just a little context for us. All right, so here's our next logical progression. This is kind of what I was alluding to at the beginning. So what happens if over our interval from A to B, the functions change their orientation, right? So in other words, for part of the graph, f is on top and g is on bottom. But then for this middle part of the graph, they change their orientation, right? And now f is the bottom function and g is the top function. And so like I said, if we're calculating area between curves, this is always going to be a positive value. If you were to integrate over this interval, so kind of maybe even think about this. If I integrated from a to b over the entire interval, and let's say, f of x minus g of x, because f starts out on top and g is on bottom. And I did that over the entire interval from a to b, not taking into consideration those 2 points of intersection where the orientation of the two functions changes. What would I actually then be calculating? What would that represent, right? Because if f is above g, as it is here and here, then that would give me kind of that idea of a positive area. All right, so just like the area, the graph lying above the x-axis previously. So where f lies above g, because if we take f of x minus g of x, f is larger than g over those two parts of the graph, those would be positive values. But then where g lies above f, if you do f minus g, that's going to give you a negative value, right? Because f is smaller than g over that middle portion of the graph. So if you integrate it from a to b over the entire interval, you're going to get a value that could be positive or could be negative in this case. And, again, what would that actually mean? What would that represent, right? So if we take positive area to mean the area where f is above g, if we take negative area to be the area where g is above f, then depending on if I get a positive or negative value, it tells me which occurs more often, I guess, right? Or which area is enclosed by more of the orientation. So it's kind of confusing. It really doesn't make a whole lot of sense to say that the area between those two curves is a negative value, right? So it depends on how you define the boundaries, right? F over g, g over f, etc. So anyway, so without getting too far off of the beaten path here, when we talk about area between curves, I said these are always going to be positive values, because we will take into account if the regions or if the curves change their orientation. And I'm going to split this interval up. So this interval from a to b would be split into multiple regions at each point of intersection between our two curves. Okay? And then we would calculate the area by taking the upper function minus the lower function, but that would change from little subinterval to subinterval. All right, so over this first interval, or this first piece, I would have f of x minus g of x. Over this second piece, I would use g of x minus f of x, because g is the upper function and f is the lower function. And that way I get a positive value out of that. And then again, over this last piece, I would go back to f of x over g of x to calculate that area. Okay? So if you have an interval, in this case, interval from a to b, where over that interval, f is greater than g for some of it and g is greater than f for some of that interval, then we're going to have to split the interval into smaller subintervals and evaluate the integral over each of those subintervals by taking the height to be the upper function minus the lower function, whichever may be. Okay? So that's a quick summary of what I'm fixing to say. So what if f of x is greater than or equal to g of x, right, for some values of x, and then g of x is greater than or equal to f of x for other values of x. And of course, the main thing there is the greater than part, not necessarily the equal part. The equal part is simply where they're going to intersect each other. So it's mainly where f is greater than g, where g is greater than f. So then we split the region into several regions, or call them subregions or subintervals if you wish, where the area enclosed between the two curves would be the sum of the areas of each of those regions, so call it a sub 1, a sub 2, a sub 3, etc. All right. But then we'll just have to calculate the area of each of those subintervals individually, where, notice I'm using absolute value here to emphasize again the fact that this should always be a positive value. So the absolute value of f of x minus g of x would mean f of x minus g of x if f is greater than g, and g minus f if g is greater than f, right? Our bottom line, like we said, it's always the upper function minus the lower function, or the top function minus the bottom function. So then that integral from a to b of f of x absolute value of f of x minus g of x dx gives us the area between the curves y equal f of x, y equal g of x, and the lines x equals a and x equals b, those limits of integration. But again, this will always be a positive value because we're taking into consideration where the orientation of the two functions changes. Okay. So this is kind of our most involved scenario with this, right? So, for example, I've got the area enclosed. I know we love our trig functions. Y equals cosine of x. I'm going to call that function f. Y equals 1 minus cosine x. I'm going to call that function g. And I'm looking at the area enclosed between those two curves on the interval from 0 to pi. So I went ahead and graphed them. There's our function f and our function g, a rough sketch. So over the interval from 0 to pi, I do obviously see that there is a point of intersection, and we're going to have to find that point of intersection, right? So like we said, we need to know where that orientation changes. Now, just a tip, and you may remember from trig, when you're graphing trig functions, right? And you always want your mode to be set to radian mode, which it should be. You shouldn't have any use for degrees in calculus anyway. But when you graph it, you may want to graph it on the trig setting. So normally we do the Z standard, zoom number 6. You may want to do the trig setting. Okay. Zoom number, actually I can forget off the top of my head, I think it's zoom number 7 is the trig setting. Just checking that real quick because for some reason I'm drawing a blank. Yeah, zoom number 7 is the trig setting, right? And that way what it does is on your x-axis, your tick marks end up being spaced by intervals of pi over 2. So instead of tick marks representing 1, it's pi over 2, pi, 3 pi over 2, 2 pi. And so it may give you a better visual as far as, any points of intersection and what those might be. But regardless, right, I do at least need to notice that over my interval, I do have a point of intersection, so we need to find it. So whether you do it graphically, which you would get a decimal approximation, I went ahead here and did an exact. We like to be exact as much as possible. So I just set my two equations equal to each other. I find the point of intersection, so cosine x equals 1 minus cosine x, which means 2 cosine x equals 1, right? We've kind of reviewed solving trig equations before, but just as a reminder, so I solved this for cosine x equals 1/2. Now again, I'm only interested in the interval from 0 to pi, so I want to know what values of x, what angles have a cosine value of 1/2 on the interval from 0 to pi, right? And if you want to reference back to your unit circle, right, 0 to pi here, and it's a positive cosine value, which means it would have to be an angle here in quadrant 1. And this goes back to our basic function values, which I've asked you many times to review and commit to memory. The cosine of pi over 3 is 1/2. So that means I'm going to have to split my interval from 0 to pi at pi over 3. Now notice on the interval, because I do have to graph these to see which one is which, on the interval from 0 to pi over 3, f is the top function and g is the bottom function. And over the interval from pi over 3 to pi, g is now the top function and f is the bottom function. So I take my integral from 0 to pi of the absolute value of cosine x minus 1 minus cosine x, and that could be written either way, but I always just do f minus g here. But the absolute value, because we have the point of intersection, we're going to have to split that into two subintervals. The first subinterval going from 0 to pi over 3 of the upper function, in that case, which is f, which is cosine x, minus our lower function, which is g, 1 minus cosine x. Plus, we've got the integral from pi over 3 to pi of now g minus f. because g is the upper function and f is the lower function. You don't have a choice here. You're going to have to split it up because you're going to have to reverse those functions to indicate which one is the upper and which one is the lower. That way you always get a positive value. Okay? And then we can evaluate, you have to evaluate each of those integrals individually. All right, so I went ahead and just did a little simplification. The first one would be cosine minus 1 plus cosine, so I get 2 cosine minus 1. Now notice I don't have the absolute value on this anymore. I took care of that by placing the upper function first and lower function second. Upper function minus lower function. So 2 cosine x minus 1 over the interval from 0 to pi over 3, and 1 minus 2 cosine x on the interval from pi over 3 to pi. And again, I did exact calculations and I also did an approximation, but you will have to approximate each integral. First one approximately 0.6849, second one approximately 3.8264, for a total approximation of approximately 4.5113. Okay? But like I said, my main concern here is just the setup of the integral. I trust you can plug that into the calculator and do an approximation on the integral. It's all about getting the integral set up. And again, taking into account if there is a change in orientation between the upper and lower functions. And then you've got to find that point of intersection. Now, like I said, you could also do this by approximations. I mean, if you graph those two functions and find your points of intersection, it would give you the decimal approximation for pi over 3, whatever that is. And then you could use that for your limits. And again, it'll be close enough for what we need. Now, all of the regions that we've looked at up to this point have all been regions that are bounded above and below by our curves. All right, now, that is what I'm interested in for your final. I will give you a question on your final similar to the ones that we just looked at, right? But I also want to show you another possibility, should you have need for this going forward. And it's also, it's useful to look at to kind of, again, make sure you're understanding exactly what the concept is versus just memorizing some process. What if instead, notice in this case, I've got two curves defined as x equals f of y. Now I'm using the function notation loosely here because these are not functions, right? They don't pass vertical line test. But what if instead of y equals something in terms of x, I have x equals something in terms of y, right? So x is a function of y, if you wish. But the idea remains the same, in that I'm looking for the area between these two curves, okay? But this time I'm bounding the region on the left and on the right by the curves, and then I've got a lower bound at C and an upper bound at D. Okay, so it'd be the same idea as integrating from left to right, but here I'm integrating from bottom to top. And then to get a positive value for the difference between the functions, I would take the function on the right minus the function on the left to give me a positive value. All right, so again, if you look at the little rectangle I have drawn in there, right, it's all about finding the area of each of those little rectangles. The height of that rectangle, right, would be the width of that, or the difference between those two functions. So I'm going to take the function on the right minus the function on the left to give me a positive height. And in this case, instead of dx or delta x, we're using delta y as the width of our rectangle. Okay. So again, I'm just going to show you this, and you may run across a couple of these in your homework, but like I said, this is not what I'm interested in for your final. I will give you a question from the final similar to the previous examples. All right, but just kind of shows you a different approach, that we're not just always limited to a certain orientation. You put this in the context of real-world applications, you don't see a whole lot of x and y axis and that type of thing. It's always in the context of what that function actually represents in terms of the boundary of your region, and that could be anything. Right? So anyway, integral from c to d, in this case, I'm saying f of y minus g of y dy, because now I'm calculating the height, quote unquote, of our region as the difference between the right function and the left function. All right, so f of y is the one I have on the right, g of y on the left. And then we're integrating from C to D, from lower to upper bound, from lower limit to upper limit. Okay, so again, in terms of like we talked about with the upper and lower, here I'm doing right and left to make sure that that's always a positive value. So in this case, I've got these two functions: find the area enclosed by x equals y squared minus 4y, and x equals 2y minus y squared. Now I have those graphed over here on the left, but being able to graph those on your calculator, right? It has to be in y equals form. So it doesn't do me any good if it's in x equals form. So here's a little trick for these, and again, if you care to look at these. Instead of graphing these two equations, we're going to graph their inverses. Remember how to do an inverse? You just reverse the variables. So I'm going to graph y equals x squared minus 4x and y equals 2x minus x squared. Graph those in y1 and y2. All right. Now, you know what the graph of x squared minus 4x looks like. It's a parabola facing up. You know 2x minus x squared is a parabola facing down. So here's y1, and here's y2. And the trick is, whichever one of these lies on top is going to be the function that lies on the right. So it's, in other words, it's still the same orientation. Since I want this to be a positive value, I want right minus left to give me a positive distance between the two curves. It's the same orientation that you get here in terms of top and bottom. All right. So if you graph it this way, it gives you a visual, or think of it in those terms. Now I know which function lies on the right and which one lies on the left, in terms of which one lies on the top and which one lies on the bottom. So it's done in the same order. Now, as far as points of intersection, that's done exactly the same way as before, right? So I could set the two equations equal to each other, solve for y. I get y equals 0, y equals 3 in this case. If you do the points of intersection here, again, you're going to be interested in those x coordinates of those points, right? So 0 and 3. And again, you could find those graphically, or you could solve it algebraically. Okay, but here, because I have the equations written y as a function of x, I'm interested in the x coordinates. Here, x is a function of y, I'm interested in the y coordinates. Okay? So I'm integrating then from 0 to 3, because my integration in this case is going this way, right? So remember, our rectangles are being formed this way. So I'm integrating from lower to upper. Right, so yeah, and then after that it works exactly the same. I mean, I set up the integral, right? So it's just a different little twist on the same idea, but it gives us a broader application. Right? So instead of just being bounded above and below, we could also bound the region on the right and on the left and integrate from bottom to top, or lower to upper, if you wish. So, but we do need to know which function lies on the right, which one lies on the left, and then we'll set up our integral as before. So I've got the integral from 0 to 3. Those are the points of intersection with respect to our y coordinates of the points, because we're integrating vertically here. Of the function on the right, which is the 2y minus y squared, minus the function on the left, the y squared minus 4y dy. Again, I just rewrote it to simplify it, but you could always, like I said, you could plug it directly into the calculator here, or simplify it and plug it in here. Now remember too, I mean, the variable is arbitrary. So when you plug this into the calculator, you can plug this in with x, right? Just like you would normally plug it in. I mean, once you set up the integral, it's just evaluating an integral. I don't care what the variable is. So plug that in as the integral, or the function y equals negative 2x squared plus 6x, and then integrate from 0 to 3. And you get a value of 9, right? So like I said, if that confuses you, and if you're not too comfortable with that, don't sweat it. I'm not going to ask you this on the final, right? But it does at least give you an idea of how this can be done with different orientations and different boundaries. Okay? And that's it for that section.